Hi everyone, today we are going to present to you our video assignment entitled of High Performance Liquid Chromatography (Hplc). So let's get started.
Hi everyone, today I will explain to you what is High Performance Liquid Chromatography, or we call it as Hplc. High Performance Liquid Chromatography (Hplc) is a modern technique widely used for separating and analyzing components in mixture. It is an advanced version of liquid chromatography, providing greater precision and efficiency. Hplc uses a column filled with tiny particles about 5 micrometer in size, which create a large surface area for molecules to interact with. These particles act as the stationary phase, while the solvent, known as a mobile phase, is pushed through the columns under high pressure. This setup ensures effective separations of the mixture components. The instrument is equipped with a detector and computer to identify and monitor when the components are separated, making it easier to collect and analyze them. In Hplc, samples are identified by comparing their radiation time. A standard compound with a known radiation time is injected, and its peak area is measured. Then a sample containing the same analyte is injected under identical conditions. If the analyte matches the standard, their radiation time will be the same, and the ratios of their peak area can be used to determine the amounts of the compound in the sample. Reverse phase chromatography, the most commonly used Hplc technique, employs a polar mobile phase and non-polar stationary phase. Other liquid chromatography methods include normal phase partitioning, non-polar mobile phase, and polar stationary phase, adsorptions, ion exchange, and size exclusion. In this experiment, the column contains a stationary phase made of C218 alkene chains chemically bonded to small silica particles, with water as the polar solvent.
Hello and Assalamualaikum. My name is Halim Hasni binti Muhammad Marzuki and my ID number is 2022606028. So now let me state the objective of this experiment in this presentation, which is there are 3 objectives. First is to determine the rotation time of standard solution, which is caffeine, and then the second one is to identify the caffeine peak in a soft drink sample, and third is to determine the amount of caffeine in soft drink sample using the response factor of method.
I will present about methodology parts in Hplc. This slide shows the level diagram of Hplc system, which include the solvent reservoir, degassing unit, pump, auto-sampler, column, detector, waste reservoir, and data system. Let's see each component and its role. First, solvent reservoir. Solvent reservoir contains the mobile phase which carry the sample through the system. In this experiment, we use a mixture of acetonitrile and water. The mobile phase play an important role in the separation of compound. Second, degassing unit. The mobile phase flow through the degassing units, which remove dissolved air or gases. This step is essential to prevent bubble formation, which can disrupt the system flow and pressure stability. Thirdly, pump. The degassed solvent is thrown into the pump, which deliver it at a precise and consistent flow rate, which is 1.0 ml per minute, and high pressure. The pump ensures the mobile phase moves smoothly through the system, enabling the effective separations. Next, auto-sampler is an automated device that introduces the sample into flow path. For the experiment, 10 microliter of prepared sample, which is Coke or Levita, is injected. The auto-sampler ensures high accuracy and reproducibility in loading the sample. The column is the core of the Hplc system where separation occurs. It contains the stationary phase which interact with the analyte in the sample. As the sample moves through the column, different components are separated based on their chemical properties and eluting at the different retention time. The separated compound flow into the detector, which monitor them. For caffeines, we use UV detectors set at 254 nanometer to identify and quantify the analytes. the detector produces signal proportional to the compound's concentration. After passing through the detector, the mobile phase and any remaining analyte flow into the waste reservoir. This prevents contamination of spill and ensures safe disposal of solvent. Finally, the data system collects the electrical signals from the detector. It processes the signals, generates chromatograms, and calculates compound concentrations based on the peaks areas and retention times. Preparation of caffeine standard solution. First stop solution, which is solution A. Step 1. Accurately weigh 10 mg of caffeine into a 10 ml volumetric flask. Step 2. Dissolve the caffeine in the distilled water. Step 3. The solution was made up to volume with distilled water to achieve the desired concentrations. Second, a working solution, which is solution B. Step 1. Pipette 1 ml of solution A into a 10 ml volumetric flask. Step 2. The solution was made up to volume with distilled water to prepare the dilute working solution. Next, sample preparations. Step 1. Approximately 10 ml of the soft drink sample, which is Coke or Levita, was poured into a small beaker. Step 2. Carbonation was removed using a magnetic stir and sonication was performed if necessary. Step 3. A 2 until 5 ml aliquot was filtered through a 0.45 micrometer pore diameter membrane filter to remove particulate matter. Hplc injection and analysis. First, calibration with standard solutions. Step 1. 10 microliter of the solution B was injected into the Hplc system to establish the retention time of caffeine. Step 2. The area peak of caffeine was measured from the chromatogram. Second, analysis of soft drink sample. Step 1. 10 microliter of the prepared soft drink sample was injected into the Hplc system. Step 2. Peak area corresponding to caffeine was measured by comparing it to the retention time of the standard solution. This methodology ensures accurate preparation, injection, and analysis of caffeine in the soft drink sample.
So now let me continue with the result and calculation for the concentration in this experiment. On to the result in this slide shows that figure 1 graph for determination of caffeine in standard caffeine. And then the figure 2 is the graph for determination of caffeine in Coke. And lastly, figure 3, which is graph for determination of caffeine in Levita. From the table, this is the analysis for the result from that use the high-performance liquid chromatography or known as Hplc. It has a yield valuable insight into the retention time and peak area of all caffeine in all samples. Successfully fulfill the experiment objective. The caffeine standard exhibit retention time of 2.482 in minutes and the peak area of caffeine is 6,245.48779. This result can be used as reference for identified in other samples. After that, the Coke sample displayed that a retention time of 2.481 minutes almost identical to the standard. This confirmed that presence of caffeine in the soft drink. Its peak area was 7,001.12305, indicate a higher concentration of caffeine compared to the standard. For Levita, it shows a retention time of 2.479 minutes, also near identical to the caffeine standard, with a noticeable higher peak area of 11,151.1000, suggesting that Levita contains significantly more caffeine than both of the standard caffeine and the Coke sample. Moving on to the next slide, we have to calculate the concentration of caffeine in ppm for the Coke and Levita sample. First of all, we have to find the RF value for caffeine standard, which is the formula is peak area of caffeine standard divided by concentration of caffeine standard. As you can see on the slide, based on the equation given, we can get the value of RF, which is 62,419.8779 mg per ml. By using this formula, peak area of caffeine in sample divided with RF value caffeine standard, we will get the concentration of caffeine in Coke sample, which is 112.03 ppm, and the concentration for the Levita sample is 178.432 ppm.
Moving on to the discussion. High performance liquid, HPLC. HPLC has the ability to separate, identify and quantitate the compounds that are present in any sample that can be dissolved in a liquid. Greater separation in a combination of molecules that include standard caffeine, coke and Levita. Compounds can be easily detected at trace concentration as low as parts per trillion, which is PPT. The tiny particles in column and large surface area to which the molecule may be adsorbed. And now moving on to the components in HPLC. The basic components of HPLC include solvents, which is mobile phase, and then we have pump to maintain constant flow rate of mobile phase through HPLC, and then we have injector to inject specific volumes into mobile phase. And then we have column, and last we have detector. Detector that we use in this experiment is UV-vis detector. The diagram that I put below in figure 1 shows the main components of an HPLC instrument. And now we talk about the normal and reverse phase. In this experiment, we obtained that reverse phase transition liquid chromatography was used. It has a non-polar stationary phase and a polar mobile phase. A non-polar molecules have stronger interactions with the stationary phase, which increases their retention time, whereas polar compounds elute more rapidly rather than non-polar compounds. And then we discuss about the gradient elution employed to enhance the separation of complex mixture by altering the composition of the mobile phase during the analysis. Change the mobile phase polarity from polar to non-polar while running the sample can reduce the retention time required for the analyte to elute through the column. And then we discuss about the concentration of caffeine in coke and Levita. Amount of caffeine in soft drink was calculated by choose the value of retention time of chromatogram that closest to the retention time in standard caffeine. The concentration in Levita is more higher than coke. Coke is more carbonated than Levita. This is because the composition of the strong eluent strength of the organic solvent in the ratio is higher than water. Levita elute first then coke, as the Levita takes shorter retention time than coke and make it have larger peak area of caffeine, while coke eluted later as it have longer retention time and make it have shorter peak area of caffeine.
For the conclusion of experiment 6, which is high performance liquid chromatography, HPLC, the retention time of standard solution for caffeine is 2.482 minutes, for coke 2.481 minutes, and Levita is 2.479 minutes. Next, peak area for caffeine is 6249.48779, meanwhile for coke 7001.12305 and Levita is 11151.10000. The last one are the concentration of caffeine are 62494.8779 mg per liter. Meanwhile, for concentration of coke is 112.03 ppm and Levita is 178.432 ppm.
That's all from us. Thank you for watching.